All right, we're going to do an example of an optimization problem. We're told that a cylindrical can needs to hold 1,000 cubic centimeters of oil. We want to find the dimensions of this can that will minimize the cost of metal used to manufacture the can. Let me go ahead and highlight that, and we'll minimize the cost. Okay. And the extra piece of information we're told is that this can needs to hold 1,000 cubic centimeters of oil. Okay. Now, again, I mentioned this before, I'll mention it here. When you see these types of problems on the homework or in an exam or in your future in life, it's not going to say, this is an optimization problem. You will, this part won't be here. You're just going to be given this problem and you need to figure out what to do. And that's often the hardest part of these types of word problems, is figuring out, what am I even trying to do? What's the method I'm doing? So let's practice looking for clues in this problem statement that tell us that we need to use optimization. Now, it might help that to know that optimization comes from the word optimal, which means like the best you can do. And so you often want to find like the maximum thing or the minimum thing or the largest thing or the smallest thing. And those are like the best you could possibly do. So here we're told to find the dimensions of a can that will minimize the cost. This is the clue that we are using optimization. Okay, we're trying to find the smallest, we want to find the dimensions that make the smallest that take the smallest amount of material. Okay, so minimize cost means we want to minimize the amount of material we want to use. Okay, so let's start by maybe sketching out a little picture here. I'm going to do my best to sketch a little can. I'll connect these. Oops. Okay, that's pretty good. There's my little cylindrical can. The dimensions of a can, so we're asked to find the dimensions, are the information you would need to know to construct this can. And that information would be the radius of the base. So I'm going to give that a name. I'll call it R. Okay. And I would need to know the height of the can. And if I had those two pieces of information, I could make this can, theoretically. Okay. All right. Now, there's a couple of things here. We should first write down an equation that describes the quantity we're trying to optimize. In this case, we want to minimize the cost of material, which means we don't really know what the material costs, but I know that if I use less of it, I'll spend more. I'll spend less if I use less material. So if I want to use less material to make this can, and let's say like, this is all kind of like filled in here. It's like, here's my can. I would like to use the least amount of surface area. Okay, so I want to make this can where the surface area is small. Okay, so this tells me, this green. No, I'll do it in orange. Sorry. Okay, minimize the cost means I want to minimize the surface area of this can. So let's go ahead and write down the equation for the area of a cylinder. Okay. So the surface area of a cylinder is going to be the area of the base, the top and the bottom, plus the area of sort of the part that wraps around. Well, the area of, the top or the bottom of the cylinder, that's the area of a circle. Okay. So maybe I'll do this like in pink here. This is a circle. I mean, I know I drew it like a little oval, but that's because I'm looking at it from the side. So this pink part is a circle and circles have area pi r squared. But for a can, I have two of these circles. I have one on the top and one on the bottom. So this also has an area of pi r squared. And then I have this little, not little, I have this like the outside of the can, okay, this part that I have kind of in a greenish color here, the outside of the can there, well, that's like, you know, if I were to unravel it, kind of has like this kind of shape. So I just pretend I like sliced through it. Now I'm trying to unravel it. If I were to lay it out totally flat, so I pretend I sliced the can down the side, and I unraveled the sides and I laid them down flat, then it would be a rectangle, right? If I'd like unfolded it, okay? Now, hopefully you can kind of see what I'm getting at here. This side of the rectangle, the long side here, is the side that was wrapping around into the circle. So it was like this part. The length of that side is going to be the circumference of this circle. It's the length around the top of the cylinder. So the length of this side here is going to be 2 pi r. And then the length of this side of the rectangle, well, that was, you know, the height of the rectangle before I unrolled it. So that's just going to be h. Okay, so now we need to put all this together. I have 2 copies of these, circles, one on the top, one on the bottom. So I have 2 pi r squared plus, and then the area of these, like the part that wraps around the can, this green part here, the area of that is 2 pi r. Okay, now I have my equation for the area of the can, the surface area, and I want to minimize this so that I'm using the least amount of material to construct my can. Okay, great. The only problem is when we minimize stuff, we usually tend to take derivatives. Right? We find the critical points, we test the endpoints and critical points, and we call it a day. But this, oh my gosh, goodness, I'm missing the h here. Okay, so the area of this green or this rectangle here is the 2 pi r times h. That's the area inside. So excuse me, I was forgetting that h here. Now I can address the problem. The problem here is that I have 2 different variables, right? I have an h and I have an r. Okay. So if I told you, take the derivative of this equation for the area, then you'd kind of be like, well, what do you mean? Because I have h here and I have r here. So like, what am I taking the derivative with respect to? So what we need to do is replace one of these variables, r or h, with an expression that's in terms of only the other variable, because I want this to just have r's or just have h's, either way. Okay. Now, how do we do that? We need to go back and read the problem again, because there's going to be more information in the problem that will help us do that. In particular, we're told that the can needs to hold 1,000 cubic centimeters of oil. This is called a constraint. So we're just saying, like, it's not just any can. This can has to have a certain volume. Okay, so this is a volume. We have a constraint on the volume of the can. The constraint tells me that the volume needs to be equal to 1,000 cubic centimeters. The volume of a cylinder is pi r squared h. It's the area of the base times the height. That's the volume. And I don't really need to give this a name because I'm not going to use that v later. So I'm going to erase that for now. What I really need to know is that pi r squared h equals 1,000. Now I can solve for one of the variables in this equation and substitute it back into my surface area equation. Now, it doesn't really matter, like at the end of the day, you'd get the same answer. It doesn't really matter which variable you choose to solve for. I tend to solve for the variable that looks the easiest to solve for. If I were to solve for r here, I would need to take a square root somewhere. That seems a little harder to me than I'd like to deal with. If I were to solve for h here, I just need to divide by pi r squared on both sides and I'm done. So let's solve for h. So here, if I divide by pi r squared on both sides, I have h equals 1,000 over pi r squared. cool. Now I know I have this expression for h. So wherever I see h in my surface area equation, namely here, I'm going to replace that h with 1,000 over pi r squared. So let's do that. So the surface area is 2 pi r squared plus 2 pi r times 1,000 over pi r squared. And remember, this used to be h. I just replaced it with 1,000 over pi r squared because of this constraint on the volume. And this came from the problem statement. So you'll go back and read the problem statement, and that's how you'll come up with this type of constraint. Okay, let's simplify this equation a little bit because I notice I have a pi here and a pi here. I have an r here. I have two r's, two copies of r here. So I can simplify this a little bit. So we want to minimize a equals 2 pi r squared plus, I'm going to multiply 2 and 1,000. So 2,000 over, the pi's cancel and one of the r's cancels. So 2,000 over r. Okay, now I need to think a little bit about how to optimize this. Here, notice that the domain of my function is dependent on this part of my equation and on the fact that I'm making a physical can. The fact that I'm making a physical can tells me that the radius is going to be bigger than or equal to 0 because I'm not going to make a negative radius can. That doesn't really make sense. But then the equation for the area tells me that actually it can't just be that r is bigger than or equal to 0. R has to actually be bigger than 0 because if I were to allow it to equal 0, I'd be in real big trouble here. So I need r greater than 0. Okay. Now, that's kind of all I can say at this point about the endpoints for now. I'm going to come back to arguing, whether we have a max or like how we know we have the absolute min. Let's go ahead and find the critical points, and then we'll argue. We'll make some arguments later. Okay, critical points. Well, critical points are where a prime of, in this case, my independent variables are. So I need a prime of r to equal 0 or be undefined. Okay, well, we decided that the area is undefined if r is 0. So one of the critical points here happens when r equals 0. Actually, before I say that, let me go ahead and just take the derivative. So let's compute the derivative. I need the derivative of 2 pi r squared. I'm going to do the power rule, bring down a 2, and that multiplies the other 2. So I have 4 pi r. Plus, I need the derivative of 2,000 over r. To help me out, I'm going to rewrite this a little bit. 2,000 over r is the same as 2,000 times r to the -1 power. So here I'm going to have 2,000 times, and then the derivative of r to the -1 is -r to the -2. So really I have that the derivative is 4 pi r minus 2,000 over r squared. And that's where I can come in and say the derivative does not exist when r equals 0. I could have argued that here because the function itself doesn't exist there. So one of the points is going to be r equals 0. It's one of my critical points, or one of the points where the derivative doesn't exist. But that point is not in the domain, so I'm not even going to need to worry about it. It's not in the domain of the original function. Instead, I want to set this expression for a prime equal to 0. So I'll have 4 pi r equals 2,000 over r squared. And I'm going to solve for r. So let's go ahead and multiply r squared onto both sides. So I have 4 pi r cubed equals 2,000. Then I need to divide by 4 pi on both sides. So I have r cubed equals 2,000 over 4 pi. Can simplify that a little bit to 500 over pi. Okay. And then I need to take the cube root. Okay. So I get r equals 500 over pi to all to the 1/3 power. This is my only, technically, this is my only critical point, critical number. Hopefully, I feel like I maybe might have made that a little bit confusing. This is my only critical number because even though the derivative doesn't exist when r equals 0, the original function is not defined when r equals 0. So that point is not even in the domain of the original function, so we're not going to include it in our critical points. So I can say this, the derivative does not exist when r equals 0, but r equals 0 is not in the domain of the original function a of r, so we don't include it as a critical number. Okay. So we are only concerned with this number here. Okay, now we need to argue that this point, that this number, is the minimum surface area. Okay. How do we do that? Well, let's think about, maybe I'll write this down. How can we tell if 500 over pi to the 1/3 is where the minimum value of a occurs? We cannot test endpoints because the domain of A is 0 to infinity. So there's nothing for us to test. There wasn't a closed interval like some other problems we've seen. So instead, let's think about what happens on a number. Let's make a little number line. And let's see what happens. This is for r. And let's say when r is 500 over pi to the 1/3, if you put that in a calculator, it's roughly 5.419. Okay. Excuse me. And I want to know what happens to A. So let's make some notes here. A was equal to 2 pi r squared plus 2,000 over r. And we had A prime was equal to 4 pi r minus 2,000 over r squared. I want to know what's happening to A around this critical point. I want to know whether A is increasing or decreasing around this critical point because I'm going to use the first derivative test. Okay. So let me rewrite A prime here. Let's get a common denominator. So I can say this is equal to 4 pi r cubed minus 2,000 all over r squared. I just got a common denominator of r squared, so I had to multiply this expression by r squared over r squared. Okay, so let's test some points that are on either side of 5.419. So if I test r equals 1, then A prime of r is going to be 4 pi minus 2,000 over 1. Now, I don't know exactly what 4 pi is equal to, but it's like around 12, right? Pi is like around 3, so 4 times around 3 is something around 12. Maybe it'll be a little more than that, but it's definitely not bigger than 2,000. So if I have something that's like less than 20 minus 2,000, that's going to be negative. Okay, so a prime of r here is less than 0, that means my function is decreasing to the left of my critical point. And if I choose a number bigger than 5.419, let's say I choose r equals 10, let's say, then a prime of r is going to be 4 pi times 10 cubed minus 2,000 over 10 squared, which is 100. 10 cubed is 1,000. And now I have 4 times pi times 1,000. So this is bigger than 4,000. It's 4,000 times 3 point something. So it's definitely bigger than 2,000. So now I have something that's, bigger than 2,000 minus 2,000. This is positive. So here a prime of r is greater than 0. So I know my function's increasing on the other side of the critical point. And that's for all values of r. So all values of r to the left of this point are give a decreasing function, or our a is decreasing. And for all values of r to the right of this point, our function is increasing. So this must be the absolute minimum. Okay. So I know, since a of r is decreasing, for all values of r between 0 and 500 over pi to the 1/3, and a of r is increasing for all values of r that are bigger than our critical number. Oh, sorry. For r bigger than that number, we know that 500 over pi to the 1/3 gives the minimum surface area. But we were asked for the dimensions of the can that minimize the surface area and therefore minimize the cost. Well, we know that one of the dimensions is that the radius is 500 over pi to the 1/3 power. And if we want to get the height, h. So I'll say, and we have h. Remember, we solved for h in terms of r. We have to go back up here and find it. H is equal to 1,000 over pi r squared. So we can go ahead and plug our value for r into that. So 1,000 over pi times r squared. Well, r was 500 over pi to the 1/3 squared gives us to the 2/3. So this is 1,000 over pi times 500. Actually, I'll just leave it like this for now. 2/3, 2/3, not 2 over 2. Okay. If you'd like, you can simplify this a little bit more. If you do a little bit of algebra, you'll get that this is equal to 2 times 500 over pi to the 1/3 power. Okay. And these would be our dimensions for our can. So let me give the dimensions with the units. The radius is 500 over pi to the 1/3 centimeters, and the height is 2 times 500 over pi to the 1/3 centimeters. And that's our answer. Okay. And if you're like, wait, where did this come from? I just had simplified this previously, like in my notes. You could leave it like this and just put centimeters next to it, and I would be totally fine with that. I just simplified it a little bit so that it was easier for me to write. Okay, that is it for this example. Let me know if you have any questions.